Welcome grade 11s and 12s. I would like to discuss question 4 in the grade 11 November 2020 paper. It's the question on electrostatics. Right. So our situation here is that we've got two charges, Q1, with a value of +4 microcoulomb. So +4 microcoulomb is 10 to the power -6 coulomb. And charge Q2 has a charge of -3 microcoulomb. So that value is -3 times 10 to the power -6 coulombs. They are placed a distance of 0.2 meters apart. Nice of them to give you that distance in meters. And they are placed on a straight line, as shown below. Point P is located 0.1 meter to the right of the -3 microcoulomb charge. So there would be no charge at point P. Question 4.1, define the electric field at a point. The electric field at a point is the force exerted per unit positive charge at that point in an electric field. Here you could have confusion because you also have the electric field. Now, an electric field is a three-dimensional force field around a charged object. So these two definitions should not be confused. Now, here we go with the fun story. The first calculation is 4.3, and it asks us, sorry, not 4.3, 4.2. It asks us to calculate the net electric field at point P. Now, electric field could be calculated using one of two equations: the force per unit charge, or we could combine this equation and Coulomb's law, where Coulomb's law is KQ1 Q2 over R squared. Combine these two equations and you get the equation on the data sheet: E equals KQ over R squared. Now, to solve this problem, I need to look at Q1. And its effect, or its electric field at point P. Now, the way the direction of the electric field at a point is determined is the direction in which a positive charge will experience a force. So the charge on Q1 is positive. So the electric field is towards the right. So this would be the direction of the electric field of charge 1. Q2 placed there is a negative charge. The direction of the electric field around a negative charge is towards the negative charge. So at P, Q2 has an electric field to the left. Electric fields are vector quantities. So if they're going in opposite directions, you need to choose your positive direction. I'm going to choose E2's direction as my positive direction, then E1's direction is my negative direction. The reason why I'm doing that is that Q2 is but 0.1 meters away from P, where Q1 is 0.3 meters away from P. I'm expecting E1 to be less or weaker than E2. You could do the calculations of the electric fields separately. So let's follow that path. So I'm going to calculate E1 first. It's KQ1 over R squared. That's 9. This value you will find on the data sheet. 9 times 10 to the 9 times Q1 is 4 times 10 to the minus 6. Divide that by 0.3 squared. And we get an answer of 4 times 10 to the 5 Newton per Coulomb, and that would be to the right. For E2, we follow the same path. E2's value would be KQ2 over R squared. So that would be 9 10 to the 9 times 3 10 to the minus 6. We don't substitute the negatives or the positives of the value of charge. We only use that to determine the direction of the electric fields, like E2 is to the left and E1 is to the right. Distance between point P and Q2 is 0.1 squared. So this value is a 2.7 times 10 to the 6, a much bigger electric field strength than E1. And it's to the left. Now we need to answer the question. The question asked for the net electric field, E net. Now then we add vectors. I'm going to say E2 minus E1 because E1 is in the opposite direction. So it's the 2.7 10 to the 6 minus the 4 10 to the 5, and we get an answer of 2.3 times 10 to the 10 to the 6 newtons per coulomb, and it is to the left. Next question, question 4.3. Says a charge of minus 8 microcoulomb is now placed at P. So they change the situation here, and the charge that they place here is -8 times 10 to the -6 coulombs. Calculate the net force on the -8 microcoulomb charge due to the +4 microcoulomb and -3 microcoulomb. Now we're going to use this equation where electric field is force per charge, per unit charge. So the electric field is the force per charge, and we want the net electric field on that charge, sorry, the net force on that charge. So we need to use the net electric field. The net electric field at that point is 2.3 10 to the 6. The net force is what we need to calculate, and the charge at that point is 8 times 10 to the -6 coulombs. It's a negative charge, so obviously the electric field, sorry, the force on the negative charge would be the opposite direction as the net electric field. So F net, if we do our mathematics here, is 18.4 newtons, and that would be to the right. The reason for that, a negative charge experiences a force in the opposite direction as the electric field, because the direction of the electric field is determined by the force on the positive charge. Right, the last question, question 4.4, is asking for a sketch graph to show the relationship between the electric field at point P and the square of the distance between the point and the charge causing that electric field. For this, we need to look at this equation. E equals KQ E equals KQ over R squared. And we need to remove the K and the Q. So E, and change it into a mathematical relationship, is the inverse of the distance squared. It's directly proportional to the inverse of the distance squared. So a graph of E in newtons per coulomb to 1 over R, sorry, to R squared, not 1 over R squared, to R squared would be hyperbolic. Sorry, R squared's unit will be meters squared. So the sketch graph would look like this. Thank you for watching the video. I hope it helps.